All right, so I'm going to get started. Hopefully everyone received the email about the grades for the midterm. I thought the scores were pretty good. I was pretty happy overall. If you have any questions about the scores or how I'm grading it, just feel free to ask me at some point. I wasn't planning on talking very much about the midterm today just because I thought people did quite well. If you did better than about 27 out of 32 on the test, you're doing quite well. But all in all, I think people are getting the material is at about the level that I'm hoping you will. So thanks for that. Are there any questions about the midterm? You will be able to get them back on Friday in discussion section. So Oliver will have them and he'll be handing them back. Yep.
How about homework?
The homework is graded.
Yeah.
You saw those? Oh yeah, right. We will also turn back homework on Friday as well. Yep. Okay. I'll go ahead and get started then. So finally we're beginning to, yeah.
Sorry, about the homework.
Yeah.
It says I have 2 dashes on mine.
If you have dashes so you don't have a grade,
Yeah.
and you turned a homework in?
I turned it into the box, right? I sent it in.
Okay, so if you do not have a grade, you should first, well, send me an email about it. There were a couple of homeworks that we have not graded yet because there were some issues with them, so maybe those were yours. So if you do not have a grade and you think you should have a grade, shoot me an email and we'll figure it out, okay? Any other questions? Okay. So this is lecture 11. Lecture 11, we're finally moving out from talking about things that are mostly you'll find in an astronomy, basically astronomy course, moving out beyond our local neighborhood and now talking about the galaxy itself. So this lecture is about the Milky Way. This picture here is actually an image of the Milky Way galaxy taken from inside, because of course we live inside the galaxy, but you can in fact create an image of what the Milky Way looks like over all sky, and that's what this is. This projection is, I think, called an ATOF projection. This is similar to sometimes you see maps of the world that are projected into this kind of shape. Okay, so you can take something that looks round and stretch it out and put it on a flat surface. This is the same thing, except for looking down on a globe, we're looking out at the sky. So it's a projected out image of the galaxy. And I'll show you some images of what the galaxy looks like in the sky and then talk a bit about then how you piece this thing together. But basically, the Milky Way galaxy, if you were to go out in a very dark place and look up at the sky, you see it as a band of stuff that's just wrapped around. And if you could walk around the entire Earth, and if it were dark, if there were no sun on the other side, you would just see this band looking like it wraps all the way around the Earth. And that's because we're embedded in a disk. And that's just what it looks like if you're embedded in a disk of stars. So, on the first day of class, I showed you this picture. And this is a picture of dawn over Central Africa. And what you see when you look out at the night sky, a sky like this, typically your eye is drawn to the bright stars and possibly the planets. But especially if you were living a few hundred years ago without lights, if there wasn't as much light pollution, the most recognizable thing in the night sky besides the moon is actually the Milky Way. Okay, if you're out someplace where it's really, really dark and you look up at the sky, especially if there's no moon, if you have a new moon or something, you will see this band stretching out overhead and is the most recognizable feature in the sky. Okay, how many people have seen the Milky Way at some point? How many people have not seen the Milky Way? Wow. Jeez. So you've never been camping or anything where like you just look out? Okay, you gotta like work hard at some point in your life to go out where there's not as much light pollution and look up, because it's like quite amazing, just the band. You can see it around here actually if you look for it. Okay, you can see if you look up at the sky, there's a part of the sky where it looks like there's slightly more glow than there are others, and that's the Milky Way. Okay, and here's the Milky Way over here in this picture. Now the interesting thing about this, it really is a recognizable thing in the sky. I'm just trying to overcome this idea that most of you guys haven't seen it. It's so sad. that it took a very long time for humans to figure out what's going on with this. It took people a long time to figure out what this was. In fact, most ancient cultures had this idea that, I talked about this before, that the world was basically a flat surface covered with this tent-like dome, okay? And maybe that was because people lived in tent-like structures, right? And what people saw the Milky Way as is basically a seam in that tent. I mean, there were some ideas that that's what it was. Not everybody. Different cultures had different ideas for what it was, but that was one idea. In other cultures, people had, in many cultures, it played a major role in their mythology. A lot of the Native American cultures in North America, the American Indians, had interesting stories involving the Milky Way, and it played a major role in some cases about, for example, souls would travel along this road in the afterlife, etc. So it's an interesting thing. Culturally, the Milky Way is pretty deep. But in terms of actually understanding physically what it is, it took people a very long time to figure out what was going on there. Here's a really nice picture of the Milky Way galaxy. A great place to see the Milky Way is actually if you ever get a chance to go to the southern hemisphere and go someplace where it's dark in the southern hemisphere. The Milky Way is gorgeous from there. Okay. It turns out that the center of the galaxy, where it's the brightest, you can see it higher overhead when you're in the southern hemisphere than you can in the northern hemisphere. It's very hard to see it from here. You can see it much better in the south. From Hawaii, you can kind of see it reasonably. You can see it reasonably well, but if you go to like Chile or South Africa or Australia or something, you can see it quite well. And here's an image, an all-sky panorama of the Milky Way as viewed from Chile. In fact, this is on top of a mountain where there are a lot of telescopes. In particular, there's something called the European Southern Observatory that has a number of telescopes up there in the Atacama Desert. And it's a great site for observing. And here you see this band of stuff stretched over the sky. Effectively what this is, right, is you've seen these panoramas before. This is someone with a camera who's taking pictures and then going all the way around. Okay, so this end of the picture matches up with some other end over here. When you do that, you see the Milky Way would actually loop up over your head and then go down like this. Okay, so and then that's stretched out on this flat picture. So you see it's just, it's quite, when it's very dark, you can see it. Now one thing that's brought out to your eye, right, is you see this glowing stuff, but then there are these dark spots. It really almost looks like clouds. If you've had the pleasure of seeing the Milky Way in a really dark sky, it will look to you like it's clouds. You'll say, oh, there's like the sky is dark and cloudy up there, even though it's not cloudy today. And then what you realize is actually it's not clouds. What this is it's gas and dust in the plane of the Milky Way that's blocking light from stars that are farther behind. And so it's basically casting a shadow into what we see. So we call it the Milky Way. We're basically getting it from these ancient Greek names for it. So as far as we're aware, pretty much all human cultures have named it something. And a lot of times it's a river or a road or something like that. And the Greeks called it Milky Band. And it's called Via Lactea in Latin for road of milk. And that's kind of where the Milky Way comes from. Okay? The Chinese call it the Silver River. You may, this Via Lactea, lactose is the Latin word for milk, right? So if you're lactose intolerant, that's what, you can't drink milk, right? So this is some lactose up here in the sky. It looks milky and glowy. But of course, the Greeks didn't really know what it was. And as I mentioned to you before, I think Galileo actually thought that the Milky Way, not Galileo, sorry, Aristotle actually thought that the Milky Way he considered the idea that the Milky Way was actually a track in the atmosphere that was burned by the sun, that the sun used to pass along this track before it now goes in a different direction. But he kind of dismissed that idea because he said, well, there's no similar track along the direction that the sun travels now. But these were the kind of ideas people were exploring for what the Milky Way was. And in general, the ancient Greeks thought that what the Milky Way was something in the atmosphere of the Earth. and not beyond the Earth itself. Are there any questions about just this kind of stuff, anything that I've said so far? So, of course, you know, I'm glad I'm showing you now lots of pictures actually taken from the ground, because, you know, like I said, if you were living hundreds of years ago, you would see this, you would have seen this thing. So here, what's shown now is a view of, what's shown over here is a view of the Milky Way as taken from Easter Island. Okay, so I like it because it sort of evokes these ancient cultures who are looking up at the sky. And this, again, this is in the southern hemisphere, so you know, you can see a number of things that you can't see from the north. I'll talk about that in a bit. So what the Milky Way really is a vast disk of stars. Okay, it is huge. And the sun is located sort of in the outer part of it, over here, next to what's called a spiral arm. But there's many spiral arms in the galaxy. And so when you look up at the night sky, you see this direction, this band. But the thing to keep in mind is every single star you see in the night sky is part of the Milky Way. Every single star you can see by eye in the night sky is inside the Milky Way galaxy. So it's a little bit confusing to then point at this band and say, oh, that's the Milky Way. Because in fact, every star you can see is the Milky Way. But what's really going on is you see more stuff along this direction than you see this direction. Okay, because you're sitting in the middle of a disk. Do people get that? So you're sitting in the middle of this disk, and there are stars up above you and below you. But there are more stars in the plane of the disk than there are up above you or below you. So when you look along the direction towards the plane, they pile up there and it just looks brighter. Okay? So that's what's going on. Now this disk of stars is immense. It's 100,000 light years across. I think I gave you this analogy before, but if you took the entire solar system out to the edge of the solar system and shrunk it down to the size of a leaf, the Milky Way galaxy would be the size of the Pacific Ocean. And the sun on this scale would be the size of a piece of pollen floating on the leaf. So 100,000 light years is huge, and the galaxy is therefore huge. Now you kind of get a sense of this when you look out at the night sky, right? There's a lot of sort of poetic images of people sitting out on a dark night just looking at the stars and thinking of the stars as innumerable. But in fact, the stars you can see by eye are not innumerable. You can count them. If you wanted to and you had the time, it's a very countable number of stars that you can see by eye at night. Even when it's really dark, the number of stars you can see by the naked eye over all of the sky is about 6,000. So there are about 6,000 stars you can see spread out over the night sky. The farthest of those is about 4,000 light years away. The Milky Way galaxy is 100,000 light years across. So what this means is when you're looking out at night, you're seeing the stars in the night sky. Every single star you can see, no matter how dark of a place you are, no matter how clear it is, are within a bubble about this big. So this is what you see. And of course, there are more stars in the plane of the disk than there are away from the plane of the disk. And that's why you have this kind of band-like feature. And there are about 200 billion stars in the galaxy. So you can see about 6,000 by eye, but in total there are about 200 billion. So your impression of just the vastness of space when you look up at the night sky is incredibly limited. It's actually much, much more vast than you think. What's more is only the brightest stars in that bubble are the ones that you can see. There are lots of stars that are just intrinsically faint. In fact, most of the stars in the galaxy are intrinsically fainter than the sun. So most of the stars, even in that bubble, you cannot see. You can only see the brightest stars in that bubble. And certainly at the edge of the bubble, 4,000 light years away, if you can see that star by eye, that's a crazy bright star and a very rare star. So you have more faint stars than you have these rare bright stars. Are there any questions about this? Yeah.
Yeah, I heard somewhere where like 2012 date we were crossing like the halfway point across the galaxy. Do you know anything about that?
Yeah, there was a lot of stuff in the media about something very special happening in 2012 associated with the sun and the earth aligning towards the galactic center and this kind of stuff. And it had to do with some things in the Mayan calendar. So the Mayan calendar kind of came to an end in 2012. And there were a lot of people who sort of got freaked out by this, thinking that, you know, they knew, somehow the ancient Mayans knew more about the universe than we do today. And that the world was going to end. And it had, part of their calendar had to do with syncing up this orientation with the galactic center in 2012. There really wasn't that much to it. The sun and the earth align in a way towards the galactic center actually quite often, pretty much every year at some level, because they go around like this. Almost all of this stuff was sort of kind of fun for people to write sort of articles in the media about, but there's really nothing that significant about it, astronomically speaking.
Does our solar system travel like around the...
Yeah, I'll talk about that. So our solar system orbits, the sun orbits around the galaxy. And I'll talk about that in a second. Yeah?
What's in the very center of the Milky Way galaxy?
What's in the very center of the Milky Way galaxy? I'll get to that in a later lecture, but basically at the very, very center we think that there's a supermassive black hole. A black hole that's about 3 million times the mass of the sun, I think is the current number. So it's very, very massive. It lives right in the middle. And it's pretty awesome, actually, some of the studies people are doing around that galactic center. So it turns out there's so much mass in that black hole in such a small region that we can see stars orbiting around it over the course of like years. So you can see stars moving and orbiting around the galactic center over the course of years. Where you think of the stars as fixed, frozen in the sky over a human lifetime, that's actually not happening in the galactic center because the gravitational field is so strong there. But I'll talk more about the black hole in the galactic center in another lecture, not in this lecture. Yeah?
Is the reason that we can see the sun during the daytime but not other stars because it's like brighter than other stars?
Yeah, so the question was, why can we see the sun in the daytime but we can't see any of the other stars? Yeah, it's just like, it's just so bright. You know, if I had a big bright spotlight and I had a candle in the room, if I just shone the spotlight right in your face, you could not see this candle here. So it's sort of like that. Except the analogy is that there's two spotlights that are about the same brightness. One of them is right in your face, and the other one is like in Oklahoma. It's sort of like that. So it's just that it's just so bright, and you can't see the stars. You can see the moon during the day, right? But the moon is just so much brighter than the stars, and that's why you can see the moon during the day, but pretty much no other stars. Okay, this is a really good representation of what we think the galaxy looks like from above, but it's not a real picture of the galaxy from above. Does anyone know why you immediately know this is not a real picture of the galaxy? Yeah.
Because we haven't escaped our galaxy, so we can't actually take a picture.
Yeah, taking a picture of the galaxy would not be a very easy thing to do because this is 100,000 light years across, right? So it would require you traveling 100,000 light years up here, taking a picture, and then getting that picture back to us. So at minimum, you're talking 200,000 years just to do it. And we can't travel at the speed of light. So it would be very hard to do that. So we're trapped in the Milky Way. So in some sense, the Milky Way is the galaxy we can study the best because we're inside of it, but it's also the galaxy that we can't study very well at all because we're trapped inside of it. It's like trying to figure out like what color your house is while staying inside your house. Like, it's not a very easy thing to do. But there's tricks we use to try to, to do this. But based on a lot of work, and I'll get to this a bit more, but it requires using light understanding the electromagnetic spectrum over all its wavelengths. Specifically, very long wavelength light is the stuff that we use to try to get a handle on what's going on the other side of the galaxy. Because there's a lot of stuff in the way to absorb light on the way to us. And I'll get to that in a later lecture. In this lecture, I'm just going to talk to you about what we know about the Milky Way now. In the next lecture, I'm going to go back and tell you the story about how we came to discover it. So discovering that we live in a disk of stars and that there are other disks of stars out there called galaxies is a really interesting story, and I think fundamental to our understanding our place in the universe at all. But I'll get to that in the next lecture. Now I'm just going to talk to you about what it's like, what the story is. So anyway, the sun is about 26,000 light years from the center of the galaxy. So the sun is here, sort of off the edge of what's called the Orion Spur spiral arm. The center of the galaxy has something called the galactic bar / the bulge. So it's sort of a technical detail about whether it's a bar or a bulge or what you call it. But basically there's dense stuff in the middle that has some configuration that looks a bit like a bar. And then the rest of the galaxy is laid out in a disk. And across those disks there are these spiral arms that spiral out from the center. And this spiral pattern in galaxies is iconic to all disk galaxies. Many disk galaxies in the universe have these spiral patterns. And it's one of the reasons why galaxies are so pretty. They have this sort of spiral shape. What else do I want to say about this? The other thing you'll notice in this picture is that these arms and other features have kind of familiar names. Okay? This thing is called the Perseus arm. As I mentioned, this is called the Orion Spur. In here, it's called the Sagittarius arm. What are those names? What's Orion, Sagittarius, etc.? What are those? There's other things in the sky that have those names. Constellations, right? And what are the constellations? Constellations are stars that, are grouped together in the sky, and they appear in different parts of the sky depending on the time of year, etc. Okay? These features in the galaxy are basically things in the galaxy that in order to see them, we have to look through the stars in those constellations to see them. So it's like we have labeled the sky by the name of the constellations that live in that part of the sky, and anything we have to look in that direction to find, oftentimes you'll name those things after the constellations. But they're not physically associated with the stars in those constellations, because in most cases those constellations are way, way, way closer to you than the things you're actually labeling with names. Okay? The stars in the constellations are all like in here. But we have to look through them to see the other stuff. And that gives you a sense of why this game is kind of hard, because you have to look past all these other stars to see stuff behind those. Okay. Now, someone asked whether the sun was going around. It is. So the sun, and in fact all the stars in the galaxy, are orbiting about the center of the galaxy, more or less, roughly in circles. The sun is orbiting about the center of the galaxy at a speed of about 200 kilometers in a second. So 200 kilometers a second is very fast, whizzing around the galaxy. But the galaxy is so big, it takes about 200 million years for the sun to go around once. So every 200 million years or so, the sun has completed a trip around the galaxy. Yeah?
Is it going in full circles, or is it spiraling inwards?
It's not spiraling inwards. It's mostly going in something close to a circle.
So it doesn't fall along the arm?
No. It turns out those arms are... It took people a long time to figure out what's going on with those arms. But these arms, we understand them now as something called a density wave. And I'll show you a movie at the end of this lecture that will talk to you a bit about some ideas about why these spiral arms exist and what they're doing. But it's almost like, an example of wave phenomenon is like, imagine you're in a traffic jam, okay, and all the cars are kind of creeping along. But then there'll be these periods where there'll be places where all the cars stop, and then where all the cars go. But that wave of stopping and going actually propagates backwards, say, from where the accident is. Let's say there's an accident. Everybody stops. And then the cars behind them, have to slow down and stop. So then you might be a mile back and stopped, but the cars that now first saw the accident have now already started going and moving along again. So you can think of there's a rate of propagation of that traffic stoppage that's going backwards from where the stoppage started. That has nothing to do with how fast your car is moving. Right? It's just like, you just have these periods where all the cars are stopped, and then the stars start going again, and they're stopping again. But that's kind of decoupled from whether or not you're stopping and going, right? So this sort of this propagation of sort of a slowdown might be traveling in the backwards direction, even though all the cars are going this way. So it's sort of the same thing with these spiral arms. What's going on is you have dense stuff in the galaxy is piling up for complicated reasons along these spiral arms, and where all the stuff piles up, gas compresses and stars begin to form. And that's one reason why they're very bright along these regions. You have a lot of places where new stars are being born along those spiral arms. Anyway, I'll talk a bit about this kind of stuff later. Okay, any questions about this? Okay, but this is the best picture we have right now of what the galaxy looks like, our galaxy. Now, if we try to go outside of our galaxy, just as an aside, we see lots of we see lots of galaxies out there that we think are sort of similar to what we believe the Milky Way is like. So here's a galaxy that's called NGC 6744. And we think that the Milky Way is very similar to this kind of galaxy. So this is one example of a Milky Way twin that we've seen. This thing's about 30 million light years from us, so it's actually fairly close in the scheme of galaxies. And you know, if you want to know what a realistic image of something like the Milky Way would be, this is pretty good. And the sun, just for scale, would be something like right in here in this galaxy. So this is a sort of a cartoon then, a picture of what we think our galaxy looks like. It's a disk of stars, much thinner than it is long. So it's about a 10-to-1 ratio. It's about 10 times farther across than it is high, maybe even a little bit more, maybe 20 or 50 to 1, depending on how you measure the height. There's a central part that we call the bulge / the bar. And it's got 200 billion stars in it. Now, most of those stars are actually faint little things that are called red dwarfs. They're red. The redness signifies them being cool, if you remember the black body temperature stuff. And typical masses of these little red dwarfs are only about 1/10 that of the sun. So most of the stars in the galaxy are actually smaller than the sun. So in that sense, the sun is not typical. The sun is massive. Only about 7% of the stars around, in our part of the galaxy are like the sun in terms of its mass and its luminosity. And then there's a tiny fraction of stars that are actually more massive than the sun, burning brighter, spitting out more energy, and are more blue than the sun. They're hotter. Question? Yep.
How do we determine where the edge of our galaxy is?
So the question was, how do we determine where the edge of our galaxy is? That's a great question. Well, it's hard, and there is no sharp edge. Okay, the distribution of stars just falls off kind of slowly, and at some point you just have to define an edge based on something. So you might say, okay, 95% of the stars are within this distance. So I'm just going to tell you that's the size. And that's kind of what I've been telling you about this for the size. There are stars that are part of our galaxy that might stretch out way, 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 way much far beyond even 100,000 light years. There might be some that go out to 1,000,000 light years that were once part of our galaxy and have been kicked out there for one reason or another. But nothing in astronomy really has sharp, well-defined edges. So what you do is you just adopt something that's reasonable. So the question of how do you know, so then how do you do this measurement? I'll talk about that a bit more in later lectures, but basically you need powerful telescopes that allow you to see stars that are faint. But you also need to understand what's going on in terms of absorption of the light from distant stars by intervening material. And that's one reason why you have to look at longer wavelengths than visible. And I'll talk about that more in the next lecture. Is that good enough? I don't know exactly what you... Yeah?
Since there's very few stars like our sun, is there any solar systems that are similar to ours?
Are there any solar systems that are similar to ours? Okay.
That function like ours, the number of planets?
Yes. Okay, so the question about solar systems beyond the Earth is not something that I'm going to talk about in this part of the course. I probably will just barely talk about solar systems outside of the sun on the last lecture in this class, which I'm going to call Life in the Universe. Okay? Our understanding of extrasolar planets, planetary systems around other stars, is actually in its infancy. Only very recently have we known about large numbers of planets around other stars. When I started graduate school, which seems like to me not long ago, but to you I guess it would seem like a long time ago, there were none known, really. There were none. No one knew of any planets around other stars that we've actually measured. Finding planets around other stars is not an easy thing to do. The stars shine very brightly compared to those planets. It's very hard to image them directly, and you have to have tricks to find them. But now we know that it turns out that we believe that most stars have planets orbiting them. As far as we can tell, there are some unique things about our solar system. What seems to be the case is that a lot of solar systems have plunging planetary orbits instead of very circular, or ours are quite circular, and many of the extrasolar planets appear to be plunging. But anyway, I'll get back to this more in probably the last lecture. We're just barely getting to the point now where we're able to detect planets that are about the mass of the Earth. It's easier to detect the more massive planets because they reflect more light, they tug on their planet star more, and that's actually a great way to look for this. And they absorb more light when they cross in front of an extrasolar planet. So it turns out the first kind of planets people were detecting were like Jupiters or things even bigger than Jupiter. And just now are we getting to the point where we're just beginning to see planets that are like the Earth. So that's one thing. In the final project in this class, I'm asking you to write a paper on some popular science news in cosmology. There's a lot of stuff in the media right now about the discovery of extrasolar planets in the galaxy and what the population of planets going around other stars is. And that would be a great thing to write a final paper on. There's a lot in the media on that right now. Okay. But anyway, for now, I'm just going to talk about stars. I'm not going to talk about planets. It's reasonable to assume that many, if not most of these stars have planets. Whether those planets are just like the Earth, whether or not those planets could have liquid water and support life, that's another question. But it's interesting to think about that in the context of how many stars we have in the galaxy. So let's back up. Let's get really close to home. Let's now go really close to home and talk about what the neighbors are, what the neighborhood is around the sun. Okay? So what this plot is sort of all the stars within about 30 light years of the sun. And down to a certain luminosity, to fairly faint luminosities that we believe we can find, there's about 56 stars within 15 light years of the sun. And in fact, although there are 56 stars, only 24 of them are single stars. The rest of them are either have a partner as a binary, and some of them even have triplets. So what we learn from this, in fact, the sun is a minority in the neighborhood, in the sense that there's only one star in the system. So what you can envision, if you wanted to pretend like there were planets around these stars that were maybe having life, you would imagine living on a planet that had two suns. That may not be such an uncommon thing for planets to have two suns. The average distance between stars in the solar neighborhood is about 6 light years. All right, that's a very long way. I'll talk a bit about that in a second. But the closest star to the sun, for us, we actually have a star that's only 4.25 light years away, and that's called Proxima Centauri. Proxima Centauri is actually too dim to see with your naked eye. You can't see it by eye. Even though it's the closest star to the sun, you cannot see it in the night sky. It's one of these little dwarf stars that's not very bright. Here's a picture of what Proxima Centauri would look like when scaled to the size of the sun. It's actually not that much bigger than Jupiter. So it's a tiny little thing compared to the sun. And it's in fact 100 times too faint to see. So we only found it because we have telescopes that can look deeply. But let's say we wanted to visit this thing. Anyway, it's dim, it's our closest neighbor. What kind of distances are we talking about? Well, let's do an experiment, one of these scaling experiments that you certainly love to do with me on your tests and your homework. You take the sun and you scale it down to the size of a golf ball. All right? Now, how far away do you think Proxima Centauri would be? How many people think that it would be just at the edge of this room? Okay. How many people think that it would be let's say, across Aldrich Park from here, if the sun were the size of a golf ball. Okay. How many people think that it would be within the city of Irvine somewhere? How many people think it would be farther away than that? Okay, the minority. So it turns out that if you do this and you scale it up, the distance to Proxima Centauri, our nearest star, is 2,500 kilometers away. In Clearwater, Florida. And it would be the size of a marble, a small marble. That's the nearest star to the sun. Okay? So if you have visions of visiting other stars in a spaceship, you should go to school and study engineering and study fusion power or something and figure out how to go really fast because it's very far away. Which you should do. You should totally do that. Going in the fastest spaceship that we have now, Voyager 1, it would take about 100,000 years to get there. Now, the nearest star that's like the sun to us is actually not that much farther away than Proxima Centauri. It's called Alpha Centauri. Alpha Centauri A. So Alpha Centauri is actually a binary star system. There's two stars, A and B, that orbit each other, and one of them is actually a lot like the sun. Alpha Centauri A is very much a sun-like star. It's a little bit brighter than the sun, etc. And it's actually, Proxima Centauri is actually bound to this pair. This pair is 11 astronomical units apart, about like the sun and Jupiter apart, orbiting around like this. And Proxima Centauri is bound to it, but it's like thousands of light years away, or thousands of astronomical units away. So it's like this kind of weird triplet that's orbiting around. But anyway, these are our neighbors. So within 5 light years to the sun, which is this huge distance scaled by this golf ball in the United States, right? It's like a golf ball at one edge of the United States, and this star system's at the other. That's how far away they are. And these are our closest neighbors. But yet, this is just a tiny, tiny sliver of the galaxy, because it's only 5 light years, bubble. And the galaxy is 100,000 light years across. So, if we back up now and we look at the galaxy on the grandest scales, the sun's 26,000 light years from the center. And around the sun, the distance between stars is something like 6 light years apart. So what you've kind of learned so far is that on this scale, it's extremely unlikely that stars collide with each other. Certainly around where the sun is. Okay? Stars running into each other is something that just does not happen in a galaxy like the Milky Way. Now, as you get closer to the center of a galaxy, the stars get more densely packed, a little bit. So the distance between stars is only like a half a light year in the bulge in the middle of the galaxy. But that's still pretty far away in the scheme of things. Only when you get really packed in right around that central black hole do you usually ever get any real interactions between galaxies. Between stars, sorry. Now, I'm not talking about stars that form, because stars form in clusters, and that's how all these binaries and triplets are actually born. But if you just think about the general distribution, they're pretty far apart. Just a few more facts to kind of tell you a bit about things. The galaxy itself is probably about 10 billion years old. So there are lots of stars in our galaxy that are older than the sun. But I would say, more or less, the sun is a typical age star in this part of the galaxy. There's stars that are older, there's stars that are younger, but 4.5 billion years is typical around our part, this edge of the galaxy. If you went into the central part of the galaxy, the stars are older. So what we think that means is that those stars have just been there longer. The center part of the galaxy started to form before the outer part. But basically there are stars that have been around in this galaxy for 10 billion years or more. We're quite sure of that. Are there any questions? So if you break the disk of our galaxy up into two components, there's the central bulge bar region. That has about 10 to the 10 solar masses of stuff. So that's about 10 billion stars-ish. And then you have about 100 billion stars living in the disk, give or take. Okay. So are there any questions? Yeah.
I have a random question, but what do we do about like the angle of galaxies compared to? Or is there even like a study like why are some galaxies like more concentrated and towards the middle and not stretched out this way? And, like,
yeah.
if that makes sense.
Okay, so the question is, I think what you're saying is you've seen pictures of other galaxies beside the Milky Way. Yeah. Some of them are disks, thin disks, and some of them are more puffy and round, like that. That will be the subject of another lecture when I talk about galaxies, because now I'm just talking about the Milky Way. But basically, I'll get to it at the end. You know, galaxies, unlike stars, have near neighbors. Okay? If the Milky Way were the size of like a silver dollar, our nearest big galaxy is called Andromeda. It's also about the size of a silver dollar, and they'd be about this far apart. Plus, they're headed towards each other. And they're going to collide in a few billion years. We know for sure now that they're going to collide in a few billion years. Now, if you have two very thin disks of stars that are basically dynamical disks where the stars are just orbiting in a plane, if you have two planes of rotating stars just slam into each other like this, that's not going to end up as two planes of rotating stars. It's just going to be a mess. So when the Milky Way merges with Andromeda, it's just going to be a big ball of stars after that. And many of the galaxies we see in the universe are in fact big balls of stars. So we think that interactions among galaxies are things that shape the morphologies and distributions of stars in those galaxies. So when you look at the shape of a galaxy, it teaches you something about how it came to be. Did you have a question, or?
Yeah. When they actually collide, do we know if they're going to be spinning, I guess, in a similar direction or the way that they will hit?
We know that. I don't know the spin orientation of M31 off the top of Andromeda off the top of my head, but I am going to talk about that. So I will show you a movie of that collision, and there's a lot of cool work on that. And I think when we see that movie, we'll see it. I actually don't remember. I should know that. This is actually what I study, but I don't know the name. I don't know the answer. And that matters a little bit for what happens, but we'll talk about it. Okay, so this is what I've told you so far, right? So this is our galaxy, pretty much. Now, this side of the galaxy, we know this pretty well. As you start extrapolating to the far side of the galaxy, you should think of it as more and more artistic, the artist's interpretation of what we think might be there. Because it's harder to see stuff on the far side of the galaxy than it is on this side of the galaxy, because we have to look through all that stuff. But more or less, this is a reasonable interpretation of what the galaxy looks like, and that's where the sun is. Stars tend to be being born along these spiral arms. And these little red spots are off, you can think of them as stellar nurseries, where stars are being born in those spiral arms. So what this means is that, we know that the sun is a star, right? The sun is a star, and it lives in a galaxy, okay? So we have one star, it's the sun. The Milky Way has 200 billion stars. So the Milky Way is one among 200 billion stars in the galaxy. And in the observable universe, there's something like 100 billion stars, like 100 billion galaxies like ours. Okay? So for many people, this kind of stuff makes you feel insignificant. Does it make you feel insignificant? I wonder. Who feels insignificant when they're faced with these numbers? Who would rather not think about it? Okay. So let me try to pitch it to you a different way, right? So we're living on this leaf that's floating, then that leaf is our solar system, that's floating in this ocean that's the size of the Pacific Ocean. On this scale, the sun is a piece of pollen, and the Earth is microscopic, right? Yet, living on this microscopic thing, floating on this galactic ocean, we've figured this out. Okay? So you're a member of the species who figured this out. And as far as we know, we are the only species who figured it out. There might be others. Right? But it's no small thing, I think. It's no small thing. It's no small thing that we know this. Okay? The ants do not know that they're living in a colony in the corner of our driveway. Right? But we've done this. And the process by which we've done it, I think, is interesting. But I think you can feel good about yourself knowing that we have figured this out. And the process of figuring it out is a triumph. So just because we don't, like, control it, certainly don't control it, we're at the whim of it. But at least we understand it. And I think we can feel good about that in that context. So let's back up even more now that we're feeling all proud of ourselves. Let's back up even more and think about the general environment now. So let's meet the neighbors again, but let's not meet the neighbors of the sun. Let's meet the neighbors of the galaxy. So in this picture, you see these two things. They look kind of like clouds in the sky. And they might kind of look like maybe pieces of the Milky Way that broke off. Okay? These are actually other galaxies. You can see these things by eye in the southern hemisphere when it's dark. In a very dark sky, if you went out to the Atacama Desert in Chile, you could look up at the sky and see these things by eye. Or if you were on Easter Island, you could see them. These are called the Large and Small Magellanic Clouds. And they're satellites of the Milky Way in much the same way that the Moon is a satellite of the Earth. They're orbiting around the Milky Way galaxy. Does anyone know why they're called Magellanic Clouds? Magellan, right, Magellan. So, you know, everything's named after the first European to see them. Okay? So Magellan, you know, sailed south below the equator and saw these things and used them to navigate, etc., right? So they're named after Magellan, but of course the people living in this part of the world could see them, you know, forever. You could see them up in the sky. So Magellan did not discover these, of course, but we call them the Magellanic Clouds. These are the two biggest satellite galaxies of the Milky Way. And they weigh something like, they have something like 100 times fewer stars than the Milky Way does, more or less. Is that right? Well, 10 to 100 times fewer stars. If you look at the distribution of satellite galaxies around the Milky Way, this is what it looks like. Okay? So if on this scale it's 100,000 light years, this is the disk of the Milky Way. And there's like 25 known satellites, little satellite galaxies that orbit around the Milky Way itself. And these are puny things for the most part. The vast majority of them are very small. In fact, they have between something like 10 million, many of them have between something like 10 million and 1,000 stars each. The largest small Magellanic Clouds actually have a bit more than that. But most of them have, some of them in fact have something like 1,000 stars each. Okay, so there are galaxies actually that have 1,000 stars in them. And they're tiny little puny galaxies that are called dwarf galaxies. And those that we know about all orbit the Milky Way. But we expect them to exist throughout the universe. It's just that we could have never discovered them unless they were this close. They're like the analogy to those little dwarf stars that we can only see when they're really close to the Earth. They're little dwarf galaxies that you can only see because when they're really close to the galaxy itself. So there's lots and lots of little galaxies and there's fewer big galaxies. But even right around us in our galactic neighborhood, there's lots of stuff. And in fact, more than half of these have been discovered in the last 10 years. So we're continuously discovering new galaxies that exist right around us. Let me go back and show you this picture. So this is a picture of the night sky turns out this is an infrared light. This is a good way to try to look through the disk and see everything in the Milky Way. This is an all-sky image, and what you see down here are the large and small Magellanic Clouds in the sky. This is the center of the galaxy. And this stuff right here, this dark band that makes it look kind of cool, that's gas and dust in the plane of the disk. So I talked about this before. Light tries to shine, but that dust catches it and absorbs it. So effectively it casts a shadow. So we're seeing basically the atmosphere of the galaxy absorbing light here. It's all smeared out in the middle and bright because there's lots and lots of stars in the middle of the galaxy. We live in this disk, okay? So imagine, you know, try to think about this in your head. It's a big disk of stars. We live in it, like here. And we're just seeing it all in project and all flattened out over the sky. Now, if you squint, you know, especially if you're in the front, you might see that there's like a little band of stuff here that's not coming out on top. There's a little sharp feature here. Can anyone see that? It's there, right? Believe me, it's there. What that is actually, it's a galaxy that the Milky Way is eating up. So there's one of these little galaxies got too close, and the Milky Way is tearing it apart. We call this galaxy Sagittarius, and that's because the center of the galaxy is towards the constellation Sagittarius. This is called the Sagittarius dwarf galaxy. It's poking out here. And if you study the stars in great detail, they're emanating from this point. You can observe that, in fact, there's a gigantic stream of stars coming from it. This is called a tidal tail. So when this galaxy got too close to the Milky Way tore it apart. This is the same analogy to the tidal forces that the moon and the earth are experiencing that make the oceans stick out a little bit, if you've ever heard about that. Well, this is a tidal force that's so strong it just rips the galaxy apart. And what happens is as this thing orbits around, it stretches those stars out on this big stream, and we can see that stream in stars today. You can see it, and it wraps all the way around the whole sky. It's coming from a distinct galaxy that the Milky Way is gobbling up. What's interesting about this is just an example of how galaxies actually live a violent history. Okay? Galaxies are constantly merging with each other and tearing each other apart. We in fact think that this probably influences the shapes of galaxies too, so what we see today. So here's a movie actually. This is some research that we did here, trying to understand what this stream does to the Milky Way itself. That little ball that's whizzing around is the sun. And up here in the corner is a countdown. That's in gigayears, billion years. Okay? So what we're doing is following the orbit of this system, and you see as it gets too close to the disk, it rips it apart. But the other thing that's happening is it's doing interesting things to the disk itself. You might have noticed that it generates spiral arms when it interacts with the disk. And so what we're seeing when we look at, I'll just play it again, we think what we're seeing when we're seeing a snapshot right now, okay? Because the ticks are, 10 million years. The time ticks in that clock are 10 million years. So all we see as a species is a snapshot of this. But what we think we're seeing is a snapshot of an event that's very violent and evolving on these kind of time scales. And so what you see is the sun is here, this is the galactic center, this is Sagittarius, and there's a big tidal stream coming down. Interestingly enough, it's almost very close to that stream of Sagittarius stars raining down on the location of the sun. Just to give you another sense of what this looks like. There's the sun going around. You see it's almost going in a circle, but not quite. There's that thing hitting us, and you see that creates kind of a spiral pattern as it loops, and then that spiral winds up as the system evolves. So what we see is that these iconic spiral arms, if you take galaxies and you kind of punch them and hit them a little bit, spiral arms like this emerge. And so it could be that events like this drive spiral patterns in galaxies. You also have a bar and a bulge and all this kind of stuff. So, the point of this is that unlike stars, which really don't interact with each other very much once they've been made, stars don't collide with each other very much. Galaxies do. And so in order to understand the lives of galaxies, We have to, in some sense, take into account their environment and understand how this merging evolves. Now, so if you back up even more, so here's the Milky Way in this local environment that I was talking about before. Now the scale is something like 10 million light years. These are all these little dwarf galaxies, and the thing that was merging with the Milky Way I was just telling you about 2.5 million light years away is the Andromeda galaxy. Andromeda looks like the Milky Way too. It's very similar to the Milky Way. It's about the same brightness. And Andromeda has its own little satellite system. But you can see by eye here that, you know, galaxies, unlike stars, have neighbors, near neighbors. And they're all tugging on each other by gravity. And much of the time, they're interacting with each other. And so this fact that galaxies collide with each other and merge is going to be fundamental for us understanding what shapes them, why they have the shapes that they do. So before I finish, let me just say something about galaxies. So the Milky Way, you know, the Milky Way is an interesting thing for us, right? Because the Milky Way is our home galaxy. If there was no Milky Way, there would be no stars around us, right? The Milky Way, you need galaxies in order to have the first stars begin to form in our neighborhood. The universe was born of nothing but hydrogen and helium, with little trace other things. You can't make complex structures out of hydrogen and helium. You need carbon to make us, right? You need nitrogen and oxygen. You need a little bit of phosphorus in your DNA. Where do those elements come from? Those elements are made in stars. The fusing processes that happen in stars as stars age and burn and eventually blow up are what gives rise to these heavier elements. So the nest bed, you know, the early galaxy made the first stars in our environment. And those stars blew up, some of them blew up and ejected heavy elements. And those heavy elements were then incorporated into the next generation of stars that formed. Remember, our sun is by far not the oldest star in the solar system. It's a multiple generation star. It's made up of stuff that was previously processed through stars. And out of that material, you have planets forming around them. And those planets can collect these heavier elements that we're all made of. Yeah?
So would that kind of mean that within the galaxy, there's a certain area away from the center of the galaxy is a habitable area in which there could be life?
Well, you know, that's pretty difficult. So, you know, the question is there an area within the galaxy where there can be life?
Or it's like a higher chance of it being like a habitable area?
You know, it could be. There could be most likely habitable zones in galaxies. Okay, but it turns out that as far as, you know, if you even if you go to the center of the galaxy where the stars are quite old, those stars are still, they have a lot of metals. That is, they have a lot of heavy elements. But it could be. I mean, there could be there could be regions in the galaxy where you're less likely to be habitable. For example, if you were right in the middle of the galaxy, you might be bathed in ultraviolet light. So much ultraviolet, so much UV radiation that it might be hard to have a stable species there. So maybe being in the outskirts of the galaxy is nice because your radiation field is lower and etc. At this point, all those ideas, like all that astrobiology kind of stuff that you're talking about, is very, very uncertain, right? We only have one example of life, okay, Earth. And if you've ever taken like organic chemistry and biology classes, you know that like that is complicated enough, right? But imagine there was an entirely different type of DNA, or so we don't know a lot of things. One thing that we base a lot of things on now is that we believe that you need liquid water. Liquid water is certainly, at least on Earth, an absolute fundamental thing for life. So when people talk about habitable zones, mostly they're talking about how far away you are from your parent stars such that you can have liquid water. It's not too hot that it doesn't boil away. It's not too cold that it doesn't freeze. So in Venus, it's too hot. There's no water at all. In Mars, it's too cold. There's water, but it's all ice. It could be that on Mars in the past, there was liquid water, and maybe there was life on Mars in the past. But right now, it's, I think, highly unlikely that there is. So anyway, it's those kind of questions that are kind of forefront now. extrapolating beyond that to like where you are in the galaxy for life is so, you know, we don't know anything about that really. But it's still fun to think about, but we don't know. Okay. I'm just trying to motivate for, you know, if you don't already care about this, you know, you should care, because this is without this galaxy you would not exist. Nothing you know would exist. So, okay. That is it, and we'll see you on Thursday.